So, hello everyone. I see that people are managing to log back in, and that's excellent. It means at least we've got internet and servers are up, and maybe we're going to be able to function a little more normally. So we've missed a week. And so what we're going to do about that is pick up where we left off, but I have, I'll be leaving a couple of things out. So there's a couple of things we just won't end up doing. I will post in Canvas an updated calendar today or tomorrow, but basically we're just picking up where we left off and continuing from there. It does mean that test dates will have to shift, and I'll try to get that posted as soon as possible. Because of the mess with servers being down and everything and internet being down last week, I did extend the Chapter 16 homework, which is now due this coming Friday. I wasn't quite sure exactly how people's internet was going to function, so do it as soon as you can. Don't let it go, but you have until Friday to get it done. Today, we're going to actually start talking about a different kind of field. Up until now, we've been talking about electric fields, and we've seen that electric fields, basically the electric fields we've talked about, are made by stationary charges that actually aren't moving. And what we're going to start talking about today is what happens when charges are actually moving. What kind of fields do they make? And the basic thing so this is up to now, fields made by stationary charges. Now, fields due to moving charges. We're going to see that moving charges now make two kinds of fields. They do make electric fields as usual, but they also make magnetic fields. And so today we're going to start talking about magnetic fields due to which end up being due to moving charges. Magnetic fields are not the same as electric fields. And so we detected electric fields by finding a charged object to put somewhere, and we could start it at rest, but then it would move under the influence of the electric field. For now, although magnetic fields do exert forces, for now, what we're going to use to talk about magnetic fields and to detect them and determine what direction they're pointing in is actually compasses. And so we're going to be talking about and actually using compasses, by which I mean the kind of liquid-filled magnetic compass you might use to tell which way north is, or to if you're do orienteering, that kind of compass. And so we're going to be using compasses to detect magnetic fields. And for right now, our operational way of measuring magnetic fields will be that a compass points in the direction of the net magnetic field at its location. So a compass points in the direction of the net magnetic field now. So why does a compass point north? Well, it points north because it points in the direction of the magnetic field that's associated with the Earth. So the Earth itself is kind of a big magnet, and it has a magnetic field surrounding it. And we'll see more about magnets on Thursday, actually. But this turns out to be kind of a useful detector. And what we're going to do in lab this week is some experiments with using compasses to measure magnetic fields and looking at the magnetic fields made by moving charges. And since it's difficult to have one moving charge, we're going to use wires in circuits to make a whole lot of electrons move at the same time. And then we're going to, and in the same direction. And then we're going to be using compasses to detect and determine the magnitude and direction of those magnetic fields. The way it'll work is that, unfortunately, we can't give you the wires and the compasses. So the TAs will actually have to do the measurements for you. And then you can, but you should see this happening. The goal is for you to see this happening, to see the compass deflecting, and then you'll use the data that we get from those experiments to actually do some simple analyses. So that's what's happening in lab. So this is kind of the third kind of field we talked about. We've talked about electric fields, which are made by charged particles, even if they're stationary. We've talked about gravitational fields, which are due to anything with mass. And this is the third kind of field we've talked about, a magnetic field. And right now, what we know it does is it affects a compass. And a magnetic field is due to moving charged, associated with moving charged particles. The symbol of a magnetic field is B, and it's a vector because it has a magnitude and direction. And I don't know why its symbol is B. And the units are Tesla, which is abbreviated with a capital T. These are the SI units, which we'll be using. So for our purposes, in terms of compasses, and this is stuff you're going to need for lab this week, if a compass needle points north, so here's a compass, its needle is pointing north, and that tells us that the Earth's magnetic field at that location is pointing in that direction. Now that may or may not be, that may be close to or far from the physical North Pole of the Earth, the pole around which the axis of the Earth around which it spins, just because the magnetic North Pole isn't exactly at the geographical North Pole, and it's going to point toward the magnetic North Pole of the Earth. And where we are at our location, so the magnetic field of the Earth is actually not actually parallel to the surface of the Earth quite. It actually is a little bit inclined. But what we measure when we put a compass on a flat surface is we're measuring the horizontal component of the Earth's field. And at our location, the magnetic field of the Earth is about has a magnitude of about 2 times 10 to the minus 5th Tesla. So that just kind of gives you a calibration for the magnitude of this kind of a thing. Now, there are various things that can make a compass not point north. If there's something else that has a magnetic field nearby the compass, then the compass is going to point in the direction of the net field, which is the field due to the Earth, which is always there, and whatever other thing it is, a wire or a magnet or something like that. So we might see a compass needle, instead of pointing north, it might point at some angle to north. We'll call the angle theta. And why is it doing that? Well, this is just adding vectors. So what's happened is we've got the magnetic field of the Earth, and the compass is pointing in the direction of the net magnetic field at its location. So we've got B net is the direction the compass is pointing. And therefore, something else must have made a magnetic field that just adds to the magnetic field of the Earth to give the net field. So this is magnetic field of something else. It could be a magnet, it could be electrons moving in a wire. And so we can actually calculate how big this magnetic field due to something else is. We know the direction just by looking at the compass. We know the magnitude from the angle. So if we call this deflection angle, so this angle, this deflection angle here is theta. And if we call it, so this is the angle theta. Well, we can see that here the relationship of the magnitudes of these two things is that the magnitude of B, I'll call it B other, the ratio of the magnitude of B other to B Earth is just going to be the tangent of that angle theta. And so if B other, if the magnetic field made by some other thing is 3 times 10 to the negative 6 Tesla, then theta is going to be equal to, so theta is going to be the arctangent of 3 times 10 to the minus 6 Tesla divided by 2 times 10 to the minus 5 Tesla, which is the horizontal component of the Earth's field here. And that would give us an angle of something like 8.5 degrees. So as long as, to get a 45-degree angle, of course, this B other would have to be equal to the magnetic field of the Earth, and various things can happen. A note here in VPython expects angles in radians. So we need, so it uses radians. And so you're going to have to just convert to radians. So you could do it this way. You could say theta is equal to 2 times pi divided by 360 times 15 degrees. Or there's even a function to do that. You can just say it's equal to radians of 15 degrees. And the in Python, tangent, the arctangent is called a tan. So if you want to do it in VPython. A physicist named Ørsted in around the early 1800s was the first person to discover that if you ran a current through a wire, it would deflect a compass. So the basic idea is this, and it's the kind of thing you'll be doing in the lab. the idea is if you put a wire that's part of a circuit that's running, lighting a light bulb or something, you have a compass pointing north and you lay the wire down on top of that compass, then the compass needle will move. So if we take a top view, so top view, here's the compass needle pointing north, if this is north. But if we, whoops, let's do this here. But if we put a wire carrying a current across, just lay it down on top of the compass, then we might see the compass needle deflect. And another interesting, and so obviously if there's charged particles moving in the wire, they're going to be moving along the wire. So the velocity of electrons in this case is either that way or that way in the wire. Interestingly, if we put the wire, so here's the needle pointing north. If we put our wire, current carrying wire this way across the compass, there's actually no deflection. And that's interesting because it suggests that the magnetic field made by these electrons is actually perpendicular to the direction of motion of the electrons. Because here's our diagram. We have the magnetic field of the Earth. So here's the diagram. Well, actually, here, let's do this way. Let's move this over here so we can actually put this where it belongs. So in this case, we have the magnetic field of the Earth. And we have the net magnetic field. So it must be that the magnetic field to the, I'll call it B wire, but it's really the magnetic field of the moving electrons in the wire, actually has to be going that way, which is perpendicular to the direction of the current. So B is actually perpendicular to the motion of the electrons. And that, so how do we understand this? So to understand this, magnetic field of a current, we need to understand the magnetic field of a single moving charge. And then figure out how many moving charges there are in the wire. So that's the agenda here for today. So let's look at a VPython program that that just shows us a physical model of the magnetic field due to a single moving proton. It's simpler to use a proton because it's positively charged. So the red sphere here is our proton moving along. And we can we can see that so the proton's moving along the x-axis at this point. And we can see that the magnetic field so the tail, again, we're using this convention, the tails of the arrows are at observation locations. And we can see that the magnetic field everywhere in space is actually changing as this proton moves. That when it's close, the magnetic field's big. When the observation location is far away, the magnetic field is small. And if we rotate our view so we're looking directly at the moving proton, we can see that at these observation locations, the magnetic field is perpendicular to the direction of motion of the proton. And it also depends on the observation location. So the magnetic field must depend on both the direction of motion of the proton and the vector pointing from the source to the observation location. And so that's that's the field of a moving proton. If this was a moving electron, we'd find that the field pointed the other direction. So if we make this an electron, then we see that we get the same phenomenon, but the field is actually pointing the other direction. Okay, if we change the charge. So the magnetic field at any observation location seems to depend on the direction of motion of the charge, the vector r from the source to the observation location, and the sign of the charge. And so those are key issues here. So how do we capture that mathematically? Oh, and Brian, you ask if you're going to get it, if you lay a wire with an AC current over a compass, would you get a different behavior? The answer is yes, but the question is, what's an AC current? So what all a DC current means is that there's a steady motion of charges in one direction. And what an AC current means is that the charges go one way and then the other way and then one way and then the other way. So they switch directions back and forth sinusoidally. And so we're going to, and whether that would affect the compass at all or not would depend on how fast it switched, because if it switched too fast, the compass wouldn't have a chance to move. So we're going to talk about currents that are steady currents in a single direction, called DC, direct current, and moving charges. And we'll define what all that means in a few minutes. Well, why is the magnetic field perpendicular? It's not perpendicular to potential. Potential is a scalar, right? So, but why is a magnetic field perpendicular to the direction of motion? I think our answer is we observe that it is. And we can capture that mathematically in various ways, which codify that. But in fact, at base, this is an experimental observation. This is an observation of the world. And what we're trying to do is capture it and try to model it and see if we understand it. And if we get our model right, then we should be able to predict magnetic fields made by various things. So here is the way we distill this perpendicular relationship mathematically. So for a moving charge, just one, the magnetic field, and again, this is we really mean the magnetic field at some observation location at some instant, and we're not explicitly writing that dependence, is equal to, not surprisingly, there's a constant. It depends on the charge of the particle. It falls off like distance squared, but the perpendicularness of this is captured by the following expression. It's the cross product of the velocity times r hat. And note that this is r hat, not r. It's not the vector r, it's r hat, the unit vector in the direction of r. And so what do these things mean? Well, mu 0 over 4 pi is, of course, a constant. It's equal to 1 times 10 to the minus 7 Tesla exactly. 1 10 to the minus 7, it's Tesla meters squared per Coulomb meter per second. Why is it exact? Because that's the way the system of units was defined. V is the velocity of the moving charge. R vector from source, the moving charge, to the observation location. Oh, well, we see why the electric field, the magnetic field of a current is perpendicular to the current, yes. And in fact, it comes from the agenda that we articulated up here, which is first to, and it'll be exactly the same as looking at the electric field of lots of charges and adding up their effects. We're going to do exactly the same thing. So what we're going to do is we're going to, if we can understand the magnetic field, describe the magnetic field made by a single moving charge, then all we need to do to figure out the magnetic field of a current is just figure out how many moving charges there are in the wire at any. And so that's, so we're going to be doing exactly the same kind of thing here. Now this equation is called, has a name, it's named after the people who wrote it down. So it's the Biot Savart, they were French physicists, law. And this is another of these things that you actually have to memorize. Because it's super important. So here is our old friend, a vector cross product. So we haven't thought about this probably for a while since angular momentum. So let's review vector cross products. So so we have this V cross R hat thing that we need to evaluate. So V cross R hat, there are two ways to do it. Remember, we can either multiply the whole thing out using the components, which is what VPython will do for you. Or we can get the magnitude and direction separately, in the direction using a right-hand rule. And that's going to be really important. So we're going to work on that some today. So V cross R hat, if we do the whole thing with components, it's going to be the X component of the final product is going to be V sub Y R hat Z minus V sub Z R hat Y. So this is B sub X. And so the X component involves Y and Z. Remember, we have this XYZ circular thing. So the X component involves Y and Z, the Y component involves Z and X. The Y component is VZ minus R hat X, VZ times R hat X minus Vx R hat Z, and the Z component is V sub X, the Y component of R hat minus v sub y, the x component of r hat. So that's one way to work it out, and sometimes that's what we'll need to do. The other way is to do the magnitude and direction separately. So v cross the magnitude of v cross r hat, remember, is going to be the magnitude of v times the magnitude of r hat times the sine of the angle between them, which in this case is going to be the magnitude of v times 1, because the magnitude of a unit vector is always 1 times sine of theta. And the direction is given by the right-hand rule. So getting directions with the right-hand rule is super, super important. And so when I had power last week, I actually wrote a little program to illustrate how we do this, which I'd like to show you. So here's VPython. Okay. So here we have, so this is an illustration of how to use your right hand to get the direction of the magnetic field at an observation location due to some moving charge. Our moving charge is positive because that just makes the signs easier for now. And we can choose the directions of the velocity and the direction of the r, the vector pointing from the source to the observation location, and then see how that works out. So here, let's make the velocity in the plus x direction. So as it says down here in the caption, the green arrow is the velocity, and the vector r is represented by a magenta arrow, and let's make r in the plus y direction. Now, the direction of v cross r is, of course, the same as the direction of v cross r hat. So for directions. Okay, so now, as usual, plus x is to the right, plus y is up, plus z is out of the page toward us, out of the screen toward us, okay? So now we need a right hand. So here's a right hand. And you can tell it's a right hand because it's wearing a wristband that says R on the back. It's like its smartwatch said R or something like that. And remember that the first thing we have to do when we do a cross product with the right hand is align our fingers with the vector that shows up first in the cross product. Now, in this case, this is v cross r hat. So we want to align our fingers with the vector v, and to do that, we have to rotate our arm, okay, to align our fingers with v. Now the next step, so now our fingers are aligned with v, and notice that our hand we're imagining our hand being at the location of this moving particle, okay? So we put our hand right where the moving particle is. It's in the middle of our palm here. Now we're going to want to fold our fingers toward the second vector, but the second vector is pointing up and our fingers aren't pointing that way. So we actually have to rotate our wrist so that it's possible to fold our fingers toward the plus y direction here. So we had to rotate our wrist, and now we can fold our fingers toward r. And now we extend our thumb, and that gives us the direction of the magnetic field, but that's the magnetic field at the observation location. So we actually kind of have to move this arrow. We can't move our thumb, but we can move the magical cyan arrow that was sticking out of our thumb to the observation location. So the result of applying the right-hand rule here was that if the velocity of the proton was in the plus x direction and we wanted an observation location on the plus y-axis, then we find that the magnetic field at that location due to that proton at that instant is in the plus z direction. Okay, so let's try another one. And let's see if we can do this. So we're going to have a pole. And what we need is, well, let's try 6 choices. Okay, so here's what the choices in the pole are going to mean. 1 is plus x, 2 is minus x, 3 is plus y, 4 is minus y, 5 is plus z, 6 is minus z. So you might want to write that down. So let's make the velocity in the plus z direction. So that's coming out toward us. And we're going to put the observation location on the negative y-axis, okay? So the proton is moving towards us. The observation location is in the negative y-axis. And the question is, what is going to be the direction of the magnetic field due to this moving proton at this instant at the observation location, which is the tip of the magenta arrow? So again, in our pole, 1 is plus x, 2 is minus x, 3 is plus y, 4 is minus y, 5 is plus z, 6 is minus z. Yeah, you really have to be willing to get your hand out and move it around here. Okay, so here's what you said. So the majority say plus x, there's a minority saying minus x, and then there's some noise here. So let's see what happens. So here's our right hand. We have to align the fingers with V. But now we're not going to be able to fold our fingers towards our hat unless we rotate the wrist. So we have to rotate the wrist. Now we can fold our fingers in the direction of R, stick our thumb out in the direction of magnetic field. And now that thumb gives us the direction of the magnetic field at the observation location. So in fact, plus X is indeed correct. So Peyton says, if it was an electron, would you use your left hand? Well, you could. What I prefer to do is to urge you to use the right hand, and then the last step would be to say, now let me check the sign of the charge. Oh, it was negative, so I have to, in fact, reverse the direction of that magnetic field. Okay, let's try one more. So let's see, V is negative Z. So we're going to, protons moving in the negative Z direction. The observation location on the negative x-axis. And so what will be the direction of the magnetic field due to this moving proton at, so plus x, plus y, plus z, minus z. Okay, we have an overwhelming vote for plus y. So let's see if that's correct. So we start with our right hand, we align our fingers with the velocity. Now, there's this rotate wrist step, and so we have to rotate our wrist so that we can curl our fingers toward R. So now we fold our fingers toward R. It's not really curling, it's folding them. And our thumb sticks straight up in the plus Y direction, exactly what you predicted. And so now we have to move that vector to the observation location. And so in fact, for velocity in the minus z direction, an observation location on the minus x-axis for a moving proton, we will indeed get the magnetic field. Good, I'm glad you find it helpful. I was trying to figure out how I could show you this on Zoom, and it just didn't seem possible. So, okay. So this program is now, well, if physicists have computer tools, then their art gets a little better, right? Okay. So anyway, so that's something that you need to be able to do. That program is now available in the GlowScript demo at glowscript.org in the Matter and Interactions demo programs there. This program is now there, and you can go and mess with it. Oh, there's one thing we didn't try. But suppose we have a situation where we've got a charge moving in the plus x direction, and we have an observation location on the plus x axis. What are we going to get for a direction of the magnetic field in that case? Well, if we use, yeah, it's going to come out to 0, isn't it? So B equals 0. And we can see it here. The magnitude of the field depends on the sine of the angle between them. But if the angle between them is 0 degrees, then in fact the magnetic field will be 0. So that observation locations on the axis of aligned with V are, you're going to get 0 magnetic field in those directions. And the same is going to be true, of course, for, yeah, exactly, sine 0, 0, as is sine of 180 degrees, right? So if we had, so here sine of 0 is 0. Here we have sine of 180 degrees is still 0. So in fact, at any location on the axis, the magnetic field is aligned with V. The magnetic field is going to be 0, and it's going to be maximum when the magnitude will be maximum when the locations, when the angle's at 90 degrees, of course, and then it'll sort of change from maximum to 0 as the angle changes. So for observation locations out here and whatnot, it'll be the same direction but a little smaller, which is what we saw in that animation of the field due to the moving proton. Okay, so just for a quick example, so we have a proton at the origin with a velocity is equal to minus 3 times 10 to the 4, 0, 0, 0 meters per second. What's the magnetic field at the observation location 0 minus 0.060 meters. So the magnitude of the magnetic field is just going to be the magnitude of mu 0 over 4 pi times the so let's write down the Biot-Savart law, which you probably haven't memorized yet. So the Biot-Savart law is the magnetic field is mu 0 over 4 pi QV cross r hat over r squared. So the magnitude of B is just going to be mu 0 over 4 pi, which is 1 times 10 to the negative 7 Tesla meters squared, Tesla meters per coulomb meter per second, I think. Let's get those units. Meters squared, right, per coulomb meter per second, times the charge, which is 1.6 times 10 to the negative 19 coulombs, times the magnitude of V cross R. So that's going to be the magnitude of V, 3 times 10 to the 4 meters per second, times 1, times the sine of 90 degrees, divided by 0.06 meters squared. And it gives us a very small number, 1.33 times 10 to the minus 19 Teslas. And so we know that from the right-hand rule, we know the direction, though. So the proton's at the origin, it's heading in the minus x direction. And the observation location is on the minus y-axis. So that means our thumb is pointing in the plus z direction. And so the actual magnetic field is going to be 0, 0, 1.33 times 10 to the minus 19 Tesla. And if it were an electron, it would point in the minus z direction, right? So we can calculate the magnetic field due to a single moving charge. And we can figure out its direction using the right-hand rule. And we do have this issue that once we've used the right-hand rule, we have to pay attention to the sign of the charge. Because if it's a negative charge, then we're multiplying by a negative number, so we have to flip the direction of the field. But what if we have a lot of moving charges? Which is what a current means. So let's remember what we know about metals. So remember that that electrons in a metal, moving charges, have a drift speed. We call that V drift. It's an average drift speed. And at equilibrium, the drift speed is 0. So there's no net motion. And the moving charges that we're in materials we're going to be talking about are almost always electrons. When a current runs in a circuit, in a wire, say, that's not equilibrium. So the drift speed is greater than 0. And if the drift speed isn't changing, we call that a steady state. It's a steady state. And we have seen that we can make currents run in circuits by hooking them up to a battery, and we could tell a current was running. We did that because we saw light bulbs light, right? So, so So here's a definition of what we're going to call electron current. It is the number of electrons per second entering a section of a conductor. So its units are going to be electrons per second. So what does that mean? Well, we've thought about wires, electrons moving through wires here. So here's a wire. And suppose that we've set up a situation where we have our electrons, the mobile electrons. Remember that in a metal, every atom gives up an electron to make this sea of mobile electrons that can move. And let's say that they're all moving to the right. So this is V. And here I'm drawing the average drift speed we're talking, okay? So how would we, what would electron current here mean? Well, if we draw a line down here and we stand here and count, we count for a second, we count the number of electrons that pass from the left of this line to the right of this line every second. And that would be the electron current, the number of electrons per second. And the kind of circuits we're working with batteries and bulbs in our sort of battery, wire, light bulb circuits. The electron current is approximately 1 times, it's going to be on the order of 10 to the 18th electrons per second passing a location. That's a lot of electrons per second, but there are an awful lot of mobile electrons in the wire, right? And we're going to use this symbol lowercase I. For electron current. So in this case, now there's another kind of current that is the kind of current that people talk about most often, which is called conventional current. And this is the number of coulombs per second. Entering a section of a conductor. But actually, it's the absolute value of the number of coulombs per second, because conventional current, which has a symbol capital I, assumes that the conductors are positive, that assumes mobile charges. So the relationship would be conventional current is equal to the the charge on an electron times the electron current here. Now, why do people talk about conventional current, and why do they assume the mobile charges are positive? This is basically due to Ben Franklin guessing wrong. So when Benjamin Franklin was doing his early experiments with currents, he realized there were that this was related to the static electricity experiments people had done before, and that there were charged particles moving in these wires, and he didn't know what they were because no one knew about electrons yet. And so he guessed that they would be positive. And so conventional current, which is the current that you'll hear most about from other people talking about wires and circuits, conventional current acts as if, assumes that what we've really got is these fictitious positive charges that are actually moving in a direction opposite to the way electrons are really moving. So we have fictitious plus charges moving opposite to electron. Now, there are a lot of situations in which this actually gives you exactly the same results, and we'll have to see what this means for magnetic fields. Because if negative charges, so a minus charge moves from here to there, so this place gets more negative and less positive. If a positive charge moves from here to there, this gets more negative, and that gets that gets more positive, and this gets more positive. So the net effect is in many cases the same. We're going to talk about electron current for a while because this is what's really going on in these wires, but we should be aware that there's this other thing. So basically, our task here is the second part of our task, which is if we can predict the magnetic field due to a single electron moving along a wire, then we should be able to predict the magnetic field due to all the electrons moving in a wire if we could just figure out how many moving electrons there are. So here's the basic issue. So here's our little piece of wire here. And here's our positive atomic cores that are sitting there and not moving. And we have this sea of mobile charges that's free to move. And if electrons are flowing in this way from the rest of the wire, and they're flowing out that way, so we want to get the number of electrons per second crossing this line, entering this section of wire. So the drift speed is v drift, and it's an average drift speed. It's not a vector. Well, in 1 second, if all these electrons are moving at a speed v, or in a time delta t, say, if all these electrons are moving in a speed v, they will have shifted over a distance v delta t. So So the electrons have all shifted here, and this distance is just v drift times delta t. So it's how far displacement in a time delta t. Now really the wire is three-dimensional, right? So what we really got is something like a cylinder here. And so this distance, so it's the electrons that were in this cylinder. They've all moved over a distance v delta t. So it's the electrons in this little disk that we're interested in. That's the number that moved in a given time delta t. And we can calculate the volume of this disk. So we know this is a distance v delta t, and we know that there's some area here of this surface, the cross-sectional area. So this is so the number of electrons in here. So if our density of mobile electrons, which is a property of the material, is n, so this is electrons per cubic meter, then the number of electrons in this disk is just the density times the volume of the disk and so that's going to be the number of electrons is going to be n times what's the volume of the disk? Well, it's the cross-sectional area times the length of the cylinder, which is v delta t. So that's the number of electrons in this disk. And so the number of electrons per second flowing past the ends is just n a v delta t divided by delta t, the time it took. And so it's just NA times the drift speed, the average drift speed. So actually the electron current in a wire is just the density of mobile electrons times the cross-sectional area of the wire times the drift speed of the electrons. So let's label this current in electrons per second. That's the density of mobile electrons. So this is electrons per cubic meter. That is the cross-sectional area of this wire. And we remember we know about cross-sectional area from way back in chapter 4, where we were thinking about stretching wires. And so that's the wire. And this is the average drift speed. So we could call it, we could put V drift here. Okay, so let's see what we can do with this. So clearly, along this line of reasoning, if we now know how many electrons per second are flowing through a wire, and we can calculate the magnetic field of one electron, then we can just multiply by the number of electrons per second moving through the wire, and we should get the magnetic field due to the whole current. So that's why we're doing this. But suppose if the electron current is 2 times 10 to the 18th electrons per second, and the diameter of our wire, the diameter is 1 millimeter, and the density of mobile electrons is 8 times 10 to the 28th electrons per cubic meter. What's the drift speed? Well, if the electron current is just NA V drift, the average drift speed, then V drift is going to be the electron current divided by the density of mobile electrons times the cross-sectional area. So that's 2 times 10 to the 18th divided by 8 times 10 to the 28th times pi times a half a millimeter squared. And we get a drift speed of about 3 times 10 to the negative 5th meters per second. That's pretty slow. So why is it this slow? Well, it doesn't have to be faster because there's so many electrons in the wire that you can get a big current, a huge number of electrons per second crossing a line, entering a section of the conductor with a tiny drift speed. So here we have a wire with electron current, so lots of electrons flowing in the minus x direction here. So again, we've got x to the right, y up, z out of the page. So due to moving electrons in this wire, can you figure out what is going to be the direction of the magnetic field at the observation location? The observation location is this x here, so it's basically in the minus y. It's below the wire in the minus y direction. Okay. So hold out your right hand and remember that these are electrons, not positive charges. Yeah, you have to take that last step. All right, let's see what you guys said. So everybody's convinced that it's either plus or minus z, but a little divided on what that should come out to. So let's see if we can do this. So we're going to point the fingers of our right hand in the minus x direction, and then we know that the vector, so the vector r, so we're going to consider an electron right here. It's going in the minus x direction. We want to curl our hands to the minus y direction. Our thumb indeed sticks out in the plus z direction, but then there's this extra step. This would be a positive charge, but the charge is actually a negative charge. So therefore, we have to actually flip the direction, and it comes out in the minus z direction. So you've got the right, I think you've got the right hand rule down. I think you just need to remember that, oh yes, and it's that Q V cross R hat. It's not just R hat. So you've got to remember the Q piece. Now we'll see in a future discussion, in fact, Thursday, that actually all the moving electrons in this wire contribute magnetic field in the same direction at the observation location. So that makes our conclusion good. No, remember that, so conventional current, remember that I is the number of electrons per second, and conventional current is coulombs per second, so that I is going to be the number of electrons per second times a plus E, which is the charge on one electron. Except that we're taking an absolute value because, yeah. So it has different units. Okay, in chat, what did you learn today that you didn't know? When people talk about electromagnetic fields, they're talking about electric and magnetic fields is what they really mean. So electromagnetic just kind of lumps together electric and magnetic fields. It turns out that, interestingly, if we think about moving reference frames, people observe different amounts of electric and magnetic fields. So there is some interesting relationship between them.
So is there only like a magnetic field created by the movement of the electrons, whereas if they're just sitting still, like still with that charge, there's no magnetic field?
That's right, and that's the first time we've seen a phenomenon that really depends on motion. So if a proton is sitting still, you will not detect a magnetic field around it, but if it's moving, then you will.
Okay, so then like with the case of just like electricity in a wire, would something like so looking at the compass, it's kind of it's fixed in one of its planes, right? So it can only move along like XZ plane, right?
Yeah, that's correct. Yeah, we've got the compass sitting on a flat surface below the surface of the Earth. There are other kinds of compasses that can move.
Yeah, so like let's say we had a compass that was three-dimensional, can point in any direction.
Yeah.
Would the wire then move it from an electric field also, like in a different direction, or no?
Compasses only respond to magnetic fields. So the difference is that the magnetic field of the Earth is not really quite horizontal here. It's inclined a little bit down, and so the Earth's field is a little bit down. The field due to the wire is going that way, so the net field would kind of be that way, and you'd see the compass needle at an angle, but it would still be just the vector sum of the,
yeah,
be pointing in the direction of the net field.
Okay, yeah, thank you.
So this might be a bit redundant, but would a electron or proton that is just rotating and not moving transitionally, does that have a magnetic field?
It turns out it does. And that's a good question. And in fact, it turns out, and we'll talk about that when we talk about magnets, but we often imagine protons and electrons to be spinning on their axes, so that just a proton sitting there all by itself has a very tiny, it looks like a very tiny magnet and does have a magnetic field, and the same for an electron. We're not actually talking about those fields right now because they're very small compared to the field made by these moving charges. But
cool. Okay, thank you.
Yeah.
And then just one more question. So we talked about before how with like electric field, it has like a travel time if it's moving, right? So is that the same amount of movement for the magnetic field over time?
Right. Yeah, so the same thing still applies, that information can't travel faster than the speed of light. So So in fact, we didn't show it in that, it wasn't a significant delay for slowly moving charges, but that moving proton, when it makes a magnetic field at some location, it actually takes a minute for that location to know that the proton's moved. So that there's actually going to be a tiny delay. So yes, I mean, if you turn off the current in a wire, say, and the electrons stop moving, you know, the magnetic field at some location will persist until there's been enough time for that information that the electrons are no longer moving to get to that location. So that retardation effect is actually exactly the same.
Okay, cool. Got you.